It's a pleasure for me to introduce you Dr. Labani Mallick. She is a National Fellow with the Canadian Institute for Theoretical Astrophysics, which is hosted at the Manitoba University in Canada, and she's also a member of the LIGO Scientific Collaboration. She has been in Canada since 2023, you just heard a few minutes ago. Before that, she got her PhD at the Inter-University Center for Astronomy and Astrophysics in India in 2019. And since she has held postdoctoral positions at Penn State University, the Indian Institute of Astrophysics, and Caltech. In this time, she has become an expert in the area of black holes across mass scales and active galactic nuclei. And as you will see in a few minutes, he has a broad range of he's addressing a broad range of topics in the AGN domain. In particular, the talk today is about constraining disk to corona power transfer function, soft X-ray excess origin, black hole split population of type 1 AGN across mass scales. And without further ado, we welcome Labani, and the floor is yours.
Yeah, so thanks for the introduction, Francisco, and thank you everyone for attending my talk. I'm really grateful to the Athena Community Office for inviting me to present our recent paper, which is on arXiv, so you can all have a read. So this paper has 3 original key points. One of them is our first ever calculation of disk to corona power transfer fraction that is applicable to any accreting objects. Another point we address in the paper is the origin of long debated soft X-ray excess in type 1 AGN. And the last point, but perhaps more impactful in the field of astrophysics in general, is the measurement of the central black hole spin in AGN across mass scales. So here you can find the detailed outline of the talk. So first, I'll give a very brief introduction to the AGN system, its ingredients, and spectral energy distribution in the X-ray band. So while describing the spectra, I will emphasize the motivation behind this research. Then I will outline our science goals and define the AGN sample that we employ to achieve those goals. And of course, I'll show you the key results derived from this work that include the origin of both hard and soft X-ray excess. And the model that we're gonna use for fitting the X-ray spectra will help us test the standard alpha disk theory. So we'll see if the disk is standard or not, or if we are missing something that is hidden in the model. And that exploration will help us calculate the disk to corona power transfer fraction for the first time in any accreting system. Not just the accretion disk, we are going to explore the properties of both hot and warm coronae. Also, broadband X-ray spectroscopy will help us constrain the spin parameter in AGN, and I'll show you the updated AGN spin versus mass plane. Then I'll discuss how we can advance the scope of this work with NewAthena. Currently, the XMM-Newton together with NuSTAR is kind of the best set of telescopes for this kind of work. But what about the future? How can we expand this work to fainter AGN populations or even AGN at higher redshift? For that, we need NewAthena. And at the end, I'll summarize our conclusions. So this is just an introductory slide on AGN because I believe there may be some students in the audience. So we can define AGN as the most luminous objects in the universe. And they are so bright that they can outshine all the stars in their host galaxy. The galaxy that is hosting an AGN is called an active galaxy. The typical range of the central black hole mass is of the order of 10 to the 5 to 10 solar masses. And nuclear luminosity is at least 10 to the 8 times the solar luminosity. Now, to describe an AGN properly, we need these 6 main ingredients. The first and the most important ingredient of an AGN is the central massive black hole. Surrounding the black hole, there is an accretion disk and X-ray plasma. We call it corona. There are 2 jets emerging from the center and extending in the outward direction up to tens of kiloparsec to sometimes even megaparsec distance. Closer to the black hole, we have a broad line region cloud, which contains high velocity gas clouds. Velocity is at least 5,000 kilometers per second. And far from the black hole, we have a narrow line region, which has low velocity clouds ranges around 100 to 500 kilometers per second. And surrounding the accretion disk, there is an obscuring torus. Now, depending on the orientation of this system relative to the observer, we can see different types of AGN. But for this work, I'll mainly prefer type 1 AGN because for type 1 AGN, the line of sight is not obscured by this molecular torus. So we can actually probe the innermost region, the central disk corona system in type 1 AGN. So for type 1 AGN, if there is no absorbing wind along the line of sight, then we see all these spectral components. Now the question is, what could be the origin of these spectral components? So in principle, all of them can be produced by reflection of coronal emission that is incident on the accretion disk. So here I need to clarify that the word reflection does not mean any kind of mirror reflection. So here the word reflection is used to describe the results of competition between emission, absorption, and scattering. So whenever I use the word reflection, it includes all these physical mechanisms. So we have the primary Pauli emission from the corona and secondary reflected emission from the accretion disk. So the intrinsic reflection spectra, which is in the gray line here, will have a forest of fluorescent emission lines in the subtexture band, a narrow iron K alpha line at 6.4 keV, and Compton hum about 10 keV. But that's not all, because we are probing the space-time just outside the event horizon of the black hole. So there will be extreme relativistic blurring of this intrinsic reflection spectrum. So what we'll see is the blur or relativistic disk reflection spectrum. So in the blur reflection spectrum, the Compton hum gets distorted. The narrow iron K alpha line turns into a broad iron K line that we see in the 5 to 7 keV band. And all these narrow emission lines in the subtexture band, they kind of blend into a single broad subtexture emission, which is mostly featureless. And we can utilize all these spectral components from the blur reflection spectrum to calculate various physical parameters. For example, spin of the black hole, density of the inner accretion disk. But the ideal way of measuring spin is to model the broad iron K line that we see in the 5 to 7 keV band. And this is one of the blur reflection features. And from this red wing of the broad line, we can clearly distinguish between different spins. But sometimes this line gets so broad and blur that we cannot even detect it. So in that case, we need to rely on other blur reflection features, for example, subtexture excess that we see below around 1 or 2 keV. And this excess emission has got huge counts as compared to the primary continuum. So it's almost always detected, even for fainter dwarf AGN. But the problem is that the origin of this subtexture emission is disputed, at least in some AGN, and we do have an alternate explanation or interpretation for it. So in the other interpretation, subtexture is produced by Compton upscattering of optical UV disk photons in a second Comptonization zone, which is a temperature much less than that of the hot corona. So this second Comptonization zone could be a transition region between the accretion disk and hot corona, possibly a warm plasma at the surface of the accretion disk, or it could be some strangely heated surface layer of the accretion disk itself. And even observationally, it has been proven by various authors that we do need this extra warm Comptonization, and reflection, blur reflection is not enough to fit the entire soft excess, in particular when the density of the accretion disk is fixed at the canonical value of 10 to the 15 per cubic centimeter. So does that mean we see this extra excess emission due to the density being fixed at the canonical value in the blur reflection model? So if we increase this density parameter, can we fit the entire subtexture excess with the blur reflection model? So this problem was tackled by Garcia et al. 2016, who basically came up with a new high density disk reflection model where density is actually a variable parameter in the model. And here you see the flux spectra calculated for variable density blur reflection model for a range of disk densities from 10 to the 15 to 20 per cubic centimeter. And clearly we can see that the model is able to boost the strength of the soft excess emission by increasing the density of the accretion disk. Now the question is why? So according to a theoretical work of Zivinson and Jersky in 1994, we can show that for a radiation pressure dominated accretion disk, the density parameter is likely to be higher than the canonical value of 10 to the 15 per cubic centimeter if we consider this fraction of power that is released from the accretion disk into the hot corona. So this fraction is called disk to corona power transfer fraction and has a range of 0 to 1. So the F equals 0 solution is still acceptable in the model, but the model fails for F equals 1 because in that case, there will be no power left in the accretion disk to be transferred to the hot corona. But anyway, if this standard disk model is valid and the inner disk is radiation pressure dominated, then we expect to see an anti-correlation between the density and black hole mass multiplied by the square of the accretion rate. And so far, this has been the case for both low and high mass AGN. But in all our previous studies, we have ignored any intrinsic scatter that may be present in other parameters, for example, this F parameter. And this ignorance may not be entirely accurate. So my motivation behind this research was to look into the finer details and get a consistent picture of the disk corona system. So here I have outlined the primary science goals of this paper. The first goal is to determine the model for soft X-ray excess. Is the high density blur reflection the final solution, or do we still need an extra warm Comptonization? Then we'll test the predictions of the standard alpha disk theory, where we are going to explore various parameter dependencies of disk density. And while doing so, we'll take a closer look at some hidden parameters that we often ignore, in particular, the disk to corona power transfer fraction. So first we'll measure it and see if it is the same in all AGN or not. So not just the accretion disk, we'll also measure the properties of the hot corona, because there are certain restrictions on the coronal property. So if those conditions are not satisfied, then we may not be able to see the inner disk reflection features. So in this context, knowing the coronal properties is also very important. And currently, broadband blur disk reflection spectroscopy with joint XMM-Newton+NuSTAR is the best method to measure the spin parameter of the central black holes in AGN, which we are going to do for the sample, which is covering almost the full range of mass. And I'll also update the existing spin versus mass plane using current spin and mass measurements from the most recent literature. So the sample that we employ for this work are all from this paper. They're all type 1 AGN. So they modeled 0.5 to 10 keV XMM-Newton spectra of 17 AGN using a preliminary version of high density disk reflection model. And they utilized only XMM-Newton observations conducted before 2016. So we selected 11 AGN from their sample that do not show any absorption, at least in the XMM CCD data, so that we can model the soft X as well and get a clear view of the disk corona system. For the selected 11 AGN, we utilize all the available XMM-Newton and NuSTAR data from the public archive. So the two key parameters that are very crucial for this work, and we need to know them beforehand, are the black hole mass and accretion rate. So here you see their distribution. The black hole masses were obtained from optical reverberation mapping, so they are quite robust measurements. And the dimensionless mass accretion rate were measured from optical luminosity. Therefore, it is expected to be much less variable over time. So this is what we see after fitting the direct continuum bands with a simple parallel model and extrapolating that model over the full range. So the ratio plot, the lower panel in each plot tells you what are the features remaining to be modeled. That include a soft X-ray excess below around 1 or 2 keV iron K emission complex in the 6 to 7 keV band. And for some sources, we see an excess emission above 10 keV. And also the strains of these features are different in different sources. So we cannot apply the same model to all of them. And we need to have a proper methodology for fitting these spectral features. So this flowchart summarizes the methodology of our spectral fitting. First, we'll start with the 3 to 78 keV hard X-ray spectra, because this band is free from the complex soft excess emission. And also, if we want to constrain the model for soft excess, we need to take care of the hard excess emission first. We cannot just directly jump and fit the soft excess. In that case, it will be an unbiased approach. So first, we model the harder X-ray part of the spectrum and then slowly move towards the softer part of it. And one thing was clear from this ratio plot, that about 10 kV, we have like two different types of sources. For one category, we do see a strong Compton hump above 10 kV, but for some sources, this hump is almost absent or like very weak. So whenever this hump is weak or undetected, then we did not use any complex distant reflection model, because that might bias the hard X-ray reflection spectrum. But in both cases, the 5 to 7 kV iron K band has either narrow iron K line or broad iron K line, or both narrow and broad iron K lines. So the presence of a broad iron K line tells you that the emission is coming from closer to the black hole. So we'll have to use the blur reflection model. So in this model, density is actually a variable parameter, and that is irrespective of the detection of Compton hump. Okay. So to fit this 3 to 78 kV hard X-ray spectra, we have got a total of 4 different models for different sources. Now, once we have the hard X-ray best fit model, we are now ready to explore the soft excess emission. So first, we extrapolate the hard X-ray best fit model to the full band and fit it with the hard band best fit model. And if blur reflection can fit the soft excess, then reflection is the origin of soft excess. And if it is not able to do that, then we need an extra warm Comptonization for it. So we have got total of 5 sets of different models from our full band spectral fitting, where for set 4 and 5, we need an extra warm Comptonization together with the high density disk reflection model. And here you see their count spectra and the best fit spectral model with all the components. For model set 1, 2, and 3, high density disk reflection, the high density blur reflection is enough to describe the entire soft X-ray excess. But for this 3 AGN, we do need an extra warm Comptonization together with the high density disk reflection. So that's the highlight here. And the coronal temperature and optical depth of the warm coronal are in this range, and they're in agreement with the standard warm coronal properties. So now we know all the models to explain various spectral components, but what about their energy-dependent variability? Because variability is an independent way to double-check their origin. So here, the first 2 plots show you the direct continuum versus disk-reflected flux in different energy bands. And we see a correlated variability in both cases between these 2 components. And we can explain this in the context of light bending model or disk reflection scenario. So when the primary X-ray source or hot corona is very close to the black hole due to strong light bending, a large fraction of rays from the hot corona will be focused onto the innermost part of the accretion disk, which produces blur disk reflection features. So if there is no change, there is no intrinsic change in the hot corona, then we expect that this reflected flux will increase as the hot coronal flux increases. And also, it is the one blur reflection that produces both the broad iron K line and soft X-ray excess. So we expect to see a correlated variability between them. And this is exactly what we are getting. So you can see a correlated variability between disk reflected flux in the soft X-ray band and the broad iron K energy band. But does that mean the warm corona is not present in the soft band? No, it only tells you that blur reflection is majorly responsible for soft X-ray excess, or at least it contributes significantly to this excess emission. So the disk reflection is inevitable, but what about the nature of the accretion disk? What are the implications of the standard alpha disk model? So there are quite a few predictions of the standard disk model, which we are going to explore now. So first, we examine the dependence of disk density on the black hole mass and accretion rate. So if this standard disk model is correct, then we expect an anti-correlation between disk density and black hole mass multiplied by the square of the accretion rate, or even with the black hole mass. But there is a restriction here. Like we see this anti-correlation when the intrinsic scatter in this F parameter is negligible across the sample. But since we are not seeing the expected anti-correlation, that means we cannot ignore the scatter in this parameter. So we will have to first calculate the parameter and see if it is the same in all AGN or not. So how do we calculate the parameter from the data? First, we measure model disk density as a function of disk radius for different values of the parameter. And then we compare that model density with the measured disk density. So here the black line is the measured disk density and the gray shaded area is its 90% confidence interval. And you see the model density agrees with the measured density for a very unique value of the parameter for every source. And the point of agreement between the model and the measured disk density is at the radius of 10 RS for every source. So we can calculate the parameter from the measured disk density at radius 10 RS. Here on the left, you see the distribution of the derived F values. The median of this distribution is around 0.7 and the range is quite extensive. So there is no point in assuming that the disk to corona power transfer fraction is the same in all AGN. And on the right-hand side, I plot the F value versus the black hole mass multiplied by the square of the accretion rate in log scale. And there we see a positive correlation between these parameters, which is expected for a radiation pressure dominated disk. So the standard disk model is not invalid. It's just that fractional power released from the disk to the corona has diverse values in the sample. So far we have explored the accretion disk in some detail, but what about the primary X-ray source or hot coronal properties? Because we are probing the disk corona system and things need to be consistent throughout. Usually a corona is characterized by two parameters, temperature and optical depth. Temperature we can calculate from, we can get from our spectral fitting, thanks to the new updated high density reflection model. In that model, both density and temperature are free parameters. So from the coronal temperature and spectral index, we can actually calculate optical depth of the hot corona. And here you see their distribution. The optical depth for the sample ranges from 0.3 to 1.6 with a median of around 0.9. So this parameter, optical depth, is a deciding parameter for the detection of inner disk reflection features. If it is too high, then we may not be able to see the inner disk reflection features well. So for the inner disk reflection features to be well observed, the optical depth of the hot corona needs to be less than 1, preferably, or at least close to 1. And our derived optical depth is in that required range. Okay, so far we have explored the disk corona system, but since black hole is the main ingredient of an AGN, so let's also probe their central black hole. Astrophysically, a black hole can be defined by two parameters, black hole mass and spin. So the spin parameter we measure from blur disk reflection features, primarily the broad iron K line and soft X-ray excess. Also in the model, we assume that the inner disk radius is at the innermost stable circular orbit. And here you see the evolution of spin as a function of mass for the central black holes in active galaxies. The blue points are mainly for high mass AGN, 36 high mass AGN, which are updated from the most recent literature. The green points are for the 13 low mass dwarf AGN from my paper published in 2022. And the red points denote our current spin measurements for the 11 AGN from this paper. That has both low and high mass AGN. Now the errors here in the spin, they are at the 90% confidence levels, although the error bars are large, but we need to consider that spin measurement is quite expensive, both in terms of data quality and modeling. But with these two papers, I'm increasing the spin sample by 40% with 24 new measurements. So far, literature has 36 spin measurements. So now in total, we have 60 spin data points. Now, using the spin distribution, we can tell whether it's the accretion or mergers as the likely formation channels of black holes. So if black holes grow by prolonged uniform accretion, we tend to get maximally spinning black holes. Whereas if they grow by chaotic accretion or mergers, we get low to intermediate spins. And here you see for some AGN, we do have low spins, which basically prefer mergers over accretion as their likely formation channel. Okay, so far we have used data from European Space Agency's XMM-Newton and NASA's NuSTAR telescopes to learn about accretion disk Coronal system, their central black holes. And they are currently the best telescopes for this kind of work, but they do have limitations because of the resolution and sensitivity. So how do we get over these limitations? The short answer is by launching NewAthena. And here you see the effective area plots for different current and proposed extra telescopes, for example, Chandra, XMM, XRISM, NewAthena, and undoubtedly NewAthena will be much more sensitive than any other telescopes. That means NewAthena will be a lot more number of photons for the same exposure time. So with NewAthena, we can explore fainter systems like dwarf AGN, low luminosity AGN, or even AGN in the early universe with much higher signal to noise ratio. Currently, the best telescope that can resolve the iron K energy band, 6 to 7 kV band, is the XRISM's Resolve spectrometer, which has a resolution of 5 electron volt. But the XIFU, extra integral field unit, onboard NewAthena will do a better job because of its resolution of 2.5 eV below 7 kV. And also it is at least 3 times more sensitive than XRISM's Resolve spectrometer. So with XIFU, we can actually resolve iron lines in much fainter AGN. Although Resolve is the best spectrometer currently for like the high resolution X-ray telescope, best high resolution X-ray telescope, but Resolve is not working below 1.7 kV. So the only telescope currently we have to probe the soft X-ray excess is the XMM-Newton, because Chandra is no longer sensitive below 0.6 kV because of its contamination in the soft X-ray band. But we can very well probe the soft excess with NewAthena, because NewAthena will be working down to 0.2 kV, and also it has much more resolution than any other telescope. So I would say for the studies of both soft excess and iron lines, no current or proposed telescopes can do a better job than NewAthena. So how is NewAthena going to advance the scope of this work? First of all, we'll achieve better accuracy in parameter estimation and faster processing due to shorter exposures than any other telescopes. And NewAthena will be very important for testing models of soft X-ray excess because of its resolution and sensitivity in the soft X-ray band. We can constrain this disk to coronal power transfer fraction for fainter AGN population. We can also constrain hot coronal temperature for higher redshift AGN, like redshift greater than 2. And finally, NewAthena will be refining spin measurements for a large number of black holes in AGN, including black holes from the early universe. So just to summarize the conclusions of this work, I would say that soft excess is well explained with the blur reflection from ionized high density disk for 70% of the sample. But for the remaining sources, we still need an extra warm Comptonization. We did not see any correlation between density and black hole mass and accretion rate. That means the scatter in this disk to coronal power transfer fraction is large across the sample, and we verified that by calculating this parameter. There we see a positive correlation between a parameter and the black hole mass multiplied by the square of the accretion rate, which is expected for a radiation pressure dominated disk. Through joint XMM-Newton and NuSTAR broadband reflection spectroscopy, we constrain the central black hole spin parameter, thereby increasing the available spin measurements in the AGN population by 20%. And most importantly, NewAthena, with its advanced sensitivity and resolution, will extend this study to fainter and even higher redshift AGN populations, thereby solving even bigger mysteries of black hole AGN formation, growth, and their evolution. So the future of X-ray astronomy is in NewAthena. So with that message, I'll stop and take any questions. Thank you.
Okay, Labani. So, are there any questions? I don't seem to see any. I have a question while people are warming up. Is that I see that in your work you have gone up to 85 kV or something like that using
78 kV.
78
Yes,
kV
right.
using NuSTAR. But Athena is not going to see much above 10, 15 kV.
Right, that's why I talked about this hot coronal temperature measurements for higher redshift AGN. So we'll have this 1 plus Z factor. So if the temperature is around, let's say, 40 kV, then it will be, like you have to just divide it by 1 plus Z. So for higher Z AGN, we can actually measure the hot coronal temperature using NewAthena. Because in that case, that temperature will fall in the below 10 kV band.
But for low redshift AGN, does it impact?
For low Z AGN, no, we can't do that with NewAthena. Only for high Z AGN.
No, I mean the study you have done for the low redshift AGN without having the sensitivity above 15 kV. How well can you compensate with the higher spectral resolution of XIFU?
Sorry, I can't hear you well. The last sentence, what did you say?
Okay, so I mean, if I got it right, you make a very detailed spectral modeling. You first modeling the hard X-rays, and then once that you have that fixed, then you look at soft X-rays.
Right.
With Athena, you don't have the hard X-rays, so you cannot do that. Can you?
But yes, that's a problem. Yes,
Okay.
I agree. Can't deny that.
Okay. Any questions, anybody? Oh, no questions yet. Well, I have more questions.
There is one
In the chat, I think.
In the chat, sorry.
It's a long question.
Sorry, I can't see. Okay, so I can't see the chat. What's happening here? Okay, let me get rid of it.
Okay, we could open the mic to the person asking the question.
Okay, yes, please.
Yeah, okay, because it's Rahat. Okay, allowed to talk. It's on the QA, okay?
There it is. Okay, so please go ahead.
Sorry?
Yeah.
Dependent are the expected advances with NewAthena on the resolution of XIFU you mentioned.
Yeah.
Okay. Okay. I think I can read the question.
Okay.
So if you look at the Prism's resolve spectra in the 6 to 7 kV band, we can actually get all these narrow emission lines. So even though XIF will have 4 electron volt, we can still do much better job than Prism's resolve spectrometer because it has slightly less resolution than Prism, right? Does that answer your question? I mean, the difference between 4 electron volt and 5 electron volts is really not much, but still, I mean, it would be at least better than resolve. That's my point here. Not worse. Yeah.
Okay, yeah, hello. Can you hear me?
Yes.
Yes.
Oh, yeah, finally. So, recently I came across an article where they were modeling the continuum emission within the plugging region of a black hole disk, like considering the excess thermal emission, because
But wait, this is not
okay,
binary system. For
okay,
AGN, we don't
like
see the disk emission.
okay, I just wanted to understand like how good that argument can be done for that AGN or something like that.
don't work here because we're
Okay.
not seeing the direct disk emission in the X-ray band. We are seeing the reflected disk emission. So what
Okay.
you're talking about the continuum fitting, that is for the binaries. So
Okay.
that, I think that argument would not work here.
Okay.
I think we have another open microphone. Yes.
No.
Okay. Says talking permitted here. Okay. Any other questions?
Shiro has a question.
Oh, yes, please go ahead.
Hello, Labani. Thanks a lot for your very clear and comprehensive talk. I was wondering, could you explain something that I might have missed? Given your calculations that you did on the F factor, this Coronal power fraction, and the estimate you did afterwards, what do you guess would be the reason of the scatter beyond the F parameter?
I don't know, maybe the geometry could be like, because the disk Coronal geometry in every source may not be the same. Some sources may have spherical, some may have slab. I don't know, like depends on like the covering fraction. How much, like how much portion of the accretion this is covered by the Corona, and the location of the Corona itself, and the distance between them as well. So there could be many, things that we don't know in detail. So, yeah.
Okay.
But I don't know whether warm corona can also be a factor there as well, because warm corona might, get some photons. Of course, it is getting photons from the accretion disk. So, a lot of possibilities.
And then I have another quick question. It is true that Athena does, for the moment, won't go beyond the 12 kV. And in general, it's kind of fairly easy to add a few points beyond this energy band. You can do it even with BAT, something above Swift and stuff like that. Depending, of course, on the flux of the source.
Right.
It shouldn't be too difficult in principle to figure out of a kind of a complementary emission, even a CubeSat or something like this. But one of the things that, for example, Chrism is showing that with high resolution, you have a better handle of the iron KV, 7 kV region.
Yes.
And that helps to see if there is distant reflection or not. So even if you don't go, say, beyond the 20 kV.
Yes. The
I mean,
reflection will be, much more constrained, even just with the 6 to 7 kV band. And then we'll have better control over the soft X's once this reflection thing is constrained with the XIFU. Yeah.
Yeah, I have the feeling that the resolution is very important because in principle, you might have ultra fast outflows or a general.
Exactly, absolutely. I'm sure they are there. We're just not able to detect using the
it's very
current.
difficult. If you have an absorption feature from a wind at slow velocity, so this means above 7 kV, which is where you have the edge of reflection, you really need the resolution in order to distinguish the two contributions. So
Yes.
from this point of view, Athena would be revolutionary.
Okay.
Absolutely. Yeah.
Thank you.
Good point. Thank you. Thank you, Chiro. Thank you, Chiro. Okay.
Okay. Any other questions? I'm looking at 3 places at the same time. Not much success there. Okay. Any other questions? Okay. Well, I have another question. Sorry. In the plot you have with A star versus mass of the black hole.
Oh, yes. Maybe I can just go to that slide. Yes.
Okay,
Oh,
so
sorry.
you have
Sorry. What's going on here? I think.
yeah.
Yes. Yeah.
Okay, so you have nicely filled up this plot with your work. I see that most have pretty high black hole spin. So I mean, following your discussion, this sort of means that mergers are not favored, right?
Yes, so there could be two things which are causing this. So high spin could be the result of high luminosity because we are mostly detecting bright AGN. Like we are measuring spin parameter mostly for bright AGN. But like, for example, if you see the dwarf AGN, they also have high spins, but they are actually their luminosity is just 10 to the 41 arcs per second. So this argument of high luminosity is having the high spin is not really correct. So you see here, the dwarf AGN is still having high spin. So I would not say it's just because of the bright AGN is having high spin. So dwarf AGN can also have high spin. And what was the question actually? Am I answering the correct question?
Is that I didn't quite get you mentioned the controversy about mergers versus sustained accretion.
Oh, okay, that one.
So can I can I get a
Yes,
statement
so
from you, or
basically
you
merging
prefer?
black holes, they actually tend to cancel out each other's spins. So the maximum spin we can obtain for merger scenario is 0.7, not above 0.7. But if it is like close to 0.9, then we can be 100% sure that it is the accretion and not the merger as the formation channel.
Okay. Thank you.
Okay.
Okay. Any more questions? Don't seem to see any. Anybody does see any questions that I'm not seeing?
No.
Q&A is
No.
empty. Let's check in the chat. I can see nothing in the chat. Okay, so I think we can let Labani get back to her work and keep producing interesting papers. So thank you very much for such an
Thank you.
interesting talk.
Thank you so
And
much.
looking forward to see your results for Athena in the future.
Yes, and I'm gonna apply for that membership by March 16th.